All right, we're doing section 6.3, which is vectors in the plane. So vectors are representative of force and magnitude, which is magnitude is the length, and direction is also described in a vector, and they look like a ray almost. So we have a point of origin, which is called our initial point. And our vector is going to go off, and this point down here is called the terminal point. We will label them as P and Q. Okay, so the way we would describe this vector would be vector PQ with a little hat on top, and the arrow, or the half arrow, is going in the direction that the vector is going in. When you see vectors denoted in writing, it's often in a lowercase bold letter. So if we have vector u, it would just be a lowercase u bolded. So like in this example, we have let u be represented by the directed line segment from point P to point Q, 0, 0 to 3, 2. That is our vector u. And v is from 1, 2. I guess I should move my label. Vector v is from 1, 2 to 4, 4. Show that u is equal to v. So if our two vectors are equal, if u is equal to v, then they would have the same magnitude. Which is distance. And the same direction, which on a graph is denoted by slope. Okay, so first we're going to find the magnitude. To find the magnitude of a vector, PQ, it's the distance formula. So the square root of second x value minus the first x value, 3 minus 0, quantity squared, plus y value, second y value minus the first y value, quantity squared. So the square root of 13 for the magnitude of vector PQ. For RS, same thing, second x value minus the first x value, quantity squared, plus the second y value minus the second x value, first y value, quantity squared, which is the square root of 13 as well. So our magnitude or direction is the distance is the same. Now we have to figure out if they have the same direction or slope. So now the slope of PQ, y2 minus y1 over x2 minus x1, 2/3. And the slope of RS, y2 minus y1 over x2 minus x1, 2/3 as well. So we can conclude that vector u is equal to vector v. Okay, we also have the component form of a vector. If it starts at the origin, it can be expressed as just the two terminal values, the terminal point, v1, v2, and it would look like little brackets instead of parentheses, v1, v2. If it starts at a different point other than the origin and ends at a different point, then you have to subtract. So the second value, the q, that's the terminal point, q1 minus p1, those are the two x values subtracted, and the two y values subtracted. That would be equal to the vector similar to up above, okay, v1, v2. Once you have a vector in component form, finding the magnitude is easier because we just take the first term squared plus the second term squared, because you essentially already subtracted the x values and the y values to get it to component form. Note here is if the magnitude of a vector v is 1, then vector v is a unit vector. And the only way that you can have a 0 magnitude is if that is the 0 vector, which is just a point at 0. Two vectors are equal only if and only if the first two values of component form are equal to the second two values of component form. So we're going to do a quick example down here, even though it's not here. So let's say we have a vector u from point P, 0, 0 to Q, 3, 2. Let's get that into component form. We get 3, 2. And we have a vector v from point R, 1, 2, to point S, 4, 4. The component form of vector v would be 4 minus 1, 4 minus 2, which is also 3, 2. So instead of doing all the work that we did on the front page, where we had to find the same distance, we had to find the same slopes, you could just find the component form of the two vectors and compare them, because these two component forms are the same, which means that our vectors are the same. Find the component form and magnitude of vector v, which has initial point 4, negative 7, and terminal point negative 1, 5. So our graph is not suited to, it doesn't fit. So we're just going to do it by hand without graphing. To find my component form first, I subtract the second x value minus the first x value, and the second y value minus the first y value. So my component form is negative 5, 12, and then it asks us to find the magnitude, which is denoted by double bars. The magnitude of vector v is the square root of the first x, the x value of component form squared, plus the y value of component form squared, and we get 13. Okay, talking about vector addition and scalar multiplication, if we have two vectors, to add them, we just add the x values and add the y values. So let's do a quick graphical approach to this. If here's my vector u, and my vector v is down here, to add them, okay, I keep vector u the same, and I move, well, this is vector v down here, and I'm going to move vector v to the tip of vector u, so it's being added on. And our resulting vector, u plus v, is, it's not very good, try again, is the resulting vector from the beginning of u to the tip of v. So this is u plus v. Okay, and scalar, if I have a vector u, a scalar is just a constant multiple, so it's just a certain number of times, oops, a certain number of times our vector u. It's just going to be longer. Okay. So if I have vector v and vector w, if I want to find 2 times vector v, I just multiply 2 into both terms of that component form of vector v. So 2 times negative 2, 5, negative 4, 10. W minus v, it's just what it sounds like. I just subtract the x values. Just 5, negative 1. And v plus 2w. I'm going to multiply 2 into my vector w. Oops. And my resulting vector is 4, 13. Okay, so here we have some rules about 3 vectors and scalars. Just all of these are facts properties that you can recall when you're doing these things. So they are commutative. Vector u plus 0 is still vector u. C times du, when c and d are both constants, you could just multiply the constants outside by themselves and then multiply by u. The distributive property holds. And the magnitude of CV, where c is a constant, you can just find the absolute value of c and multiply by the magnitude of our vector v. The associative property holds. Inverse property holds, so this is 0. And we can distribute this as well. If we have a vector out front, we can still distribute. And this is the identity, where 1 times u is still u. To obtain a unit vector in the same direction as any given vector v, we divide it by its length or magnitude. So we would take any vector v and divide it by its magnitude, and that will give us a unit vector of length 1. So I want to find a unit vector in the direction of negative 2, 5, and I want to verify that it has a magnitude of 1. So first I need to find the magnitude of vector v, which is the square root of negative 2 squared plus 5 squared, or the square root of 29. And then I just need to divide my vector v by its magnitude. So negative 2 divided by the square root of 29, 5 divided by the square root of 29, and I can't leave an answer like that ever, so I need to multiply by the square root of 29 over the square root of 29. And that's my answer for the unit vector. Now to prove that it has a magnitude of 1, I take the component form, square both terms. You could have also left it in this form too if you'd rather not have all the extra 29s everywhere. This turns into, if you simplify it, 4 29ths plus 25 29ths, which is 29 29ths, or 1. So it does, in fact, have a magnitude of 1. The standard unit vectors are I and j. I is in the direction of x, j is in the direction of 1. And to turn any vector into i's and j's, we have to have it in component form. And then we multiply the x value by 1, 0 and the y value by 0, 1. Really all you're doing is taking the x value and putting an I on it, and the y value and putting a j on it, and then adding them together. This is called a linear combination of any two vectors. And any vector can be written in a linear combination of i's and j's. So first example, we have a vector that's not in component form yet. It has initial point 2, negative 5 and terminal point negative 1, 3. Write it as a linear combination of our standard vectors I and j. I first need to get it into a component form. So negative 1 minus 2, 3 minus negative 5. Negative 3, 8. And then as a linear combination, I add an I onto the x value and a j onto the y value and add them together. That's my answer. Okay, here we are doing some operations with linear combinations. If I have vector u and vector v in linear combination form, find 2u minus 3v. I'm going to do it the same way I did before. The only difference is this time I'm going to have some like terms that I'm going to have to combine in the end. Okay, so now I have i's and j terms, so I'm going to combine them. And I'm done. All right, then that was section 6.3 on vectors.